Okay, so the lecture is being recorded now. So this is lecture number 33. So in the previous lecture, which was on Monday, we started talking about the compute architecture of GPUs. So I mentioned that in the architecture section, we will be talking first about the compute architecture and then about the memory architecture. So this is about the compute architecture of GPUs. So if you look at the GPUs physically, compute wise, so you will see units called streaming multiprocessors, SMs as we call them. So the architecture is like these SMs have certain number of cores on them, and these cores on a given SM share some control and memory between them. So depending on whether the compiler controls it or you control it, you will want some variables to be sitting on the memory which is on SMs as compared to the global memory of the GPU, which is the typical DRAM of a GPU, because of reasons that things nearer to cores are faster, as we will discuss in the lecture tomorrow on memory architecture, but this is about compute architecture. So we give you an example that for example the V100s we have on Param Himalaya have a total of 5120 cores, which is basically 80 streaming multiprocessors with 64 cores each on each SM. So then we also talked about the idea of blocks versus SM. So blocks are units of threads being supplied to the hardware to execute, whereas SMs are physical units available on the hardware. So there has to be some mapping between the SMs and the blocks. So typically you will have one SM catering to multiple blocks, and typically I mean depending on the architecture, so the blocks are generated depending on what you decide. If you remember that there was a kernel call where you had to supply the number of blocks and the number of threads per block. So that is something that the programmer or the user decides, whereas the hardware available on the GPU is dependent on what GPU you are running on. So if you run it on a very big GPU, then you will have all the blocks being given to a given SM, whereas if you have a very basic laptop like a GPU, then you will have some blocks that go into SMs, and then there has to be another pass where once the SMs are done with the initial blocks, they deal with the other blocks. So this kind of freedom is there depending on what hardware you have. But there is some difference between the threads which are running on one block as compared to threads running on the other block. So threads which are running on a given block, they can do some sort of synchronization between them. So the communication between threads within a block is much closer or much tight rather than the communication happening between threads between different blocks. Okay. We talked about barrier synchronization, so I will not repeat that again. So as I said that if you have a device which has fewer number of blocks possible because of a smaller SM, then you will have blocks. So this arrow is the direction of time. So you will have 2 blocks at a given time, for example, but if you go to a bigger GPU, then you can have more number of blocks at a given time. So this is simply block scheduling. So now we will talk about something called WOPs, another terminology in GPUs. So we said that blocks can execute in any order, okay, in the sense that you do not have control. So if you break a program into different blocks, break the job into different blocks, then which block goes first? Let's think of the matrix multiplication. So it was one element of A times B, that is the matrix P, was going to one thread. So the question is which threads or which elements of the matrices are done first in time? Well, you do not have control over that, okay. So they can execute in any order. It is like when you parallelize the loops using OpenMP. So you break the loops into different sub indices which go to different cores. So you will not have control in this case as to which indices get executed first. So which blocks get executed first. But the question is the threads inside the block. So let us say one block goes first as compared to the other block, but the question is within the block you have some threads. So which threads in a block execute first, or is there any order of execution in the threads? So this is where the idea of WOPs comes into the picture. So warps are units of 32 threads each. Okay, so if a block has 64 threads, for example, then we'll say that the block has 2 warps in it. Okay, so this is again till now it's a fixed number that till today we have 32 threads available in a given warp. So here's an example. So if you have 3 blocks that are being sent to a given streaming multiprocessor and each block has 256 threads, so that will be 8 warps in a block. So then we'll say that 24 warps are executed or are transferred to one streaming multiprocessor. Okay. Now what happens if, so we are saying that one warp is 32 threads, but the question is what happens if you have a block which has a size which is not a multiple of 32. Okay. So in that case what happens is, because the way it's organized, that warps, integral number of warps are sent. So if your block, for example, has 32 plus 16, 48 threads. If a block has 48 threads, so basically it will generate 2 warps of threads, that's 64. So the remaining 16 threads will be sitting vacant, will not be doing anything. Okay. But the question is, what is the idea of a warp? Okay. So the idea of a warp is this single instruction multiple data, SIMD, like you have in a CPU architecture, although we didn't talk much about it, but you have vectorized operations. So everything happens at one go. So a single instruction multiple data, sometimes you also call it, in this case of GPU, single instruction multiple threads. So you send one instruction and all the warps executed in one go typically. So that is the warps definitely are working in parallel. I said blocks can execute in any order, but the unit warp, which is 32 threads, will happen at one go in terms of time. Okay. But there is a situation which is an exception. So let's this idea is called control divergence. So let's look at this figure that we have on the board. So you have a condition that if thread ID is less than 24, you do the logic A, else you do the logic B. So there is a different execution path depending on the if else statement here. So in this case all the warps cannot execute in one pass. The reason is, let's say you have 32 warps, 32 threads in a given warp. So what happens is, out of these 32, 24 from 0 to 23 they execute the logic A. But when one the way if else works is that when in a given warp you reach a situation where some of the threads have to execute the logic A, which is represented in green here, then the threads which are not executing the green logic or the then logic in if become inactive. So 24 work in parallel at the same time, but the remaining 16 are sitting, sorry the remaining 8 are sitting. But in the second pass the logic B executes, so these 24 threads are inactive and the remaining 8 execute the else logic, which is represented in orange, and that all the threads have done their work. So this is called control divergence. So if you have an if else condition, things get slowed down a bit. Recently, from in the recent, earlier this is what used to happen, but in the recent architectures it is possible. They again depends on the compiler, that in some situations the different passes can happen I mean, they can happen concurrently. So the compiler decides that okay, 1 to 24 or 0 to 23, the first 24 threads have to execute some logic, and the remaining 8 have to execute the other logic, which is sort of different instruction. So it handles that. But typically, multiple passes have to be, you have to go through multiple passes if you have the situation of control divergence. And this is all important because with GPU parallelized code, you have to have a better control over things to make them faster. So in this course, the way we are discussing, we will not go into, we will not go deep into programs which have all these implemented, but it's worth knowing these things if you want to do something more useful with GPUs in general. Now, what about if each thread is executing different number of loop iterations? So, for example, if you look at this figure on the bottom right, you see that you have a certain number of threads, and each thread is doing some executions of a loop, but some threads finish early and the other threads take longer. So the question is, how does it get implemented on the WOP level? So whenever all of them are working together, the complete WOP is active. But when you reach a situation where some of the threads are done, so then a whole warp is launched, but those threads which are not expected to do anything because the loops are done, they will just become inactive. Okay. Now we come to something called instruction pipelining, which is again also implemented on a CPU level. So typically, if the compiler has to generate some number of WOPs for a given streaming multiprocessor, which is the hardware unit on GPU, it generates more threads or more WOPs than the number of cores available. So cores are the physical units, and threads are the independent amount of work to be done. So typically you would expect that if you have 64 cores available on a given streaming multiprocessor, 64 threads should be generated, but the compiler generates many more threads as compared to the number of, in fact typically it's now 16 to 32 times more threads are scheduled on a given streaming multiprocessor. So the question is, why is it? Why is the compiler generating more work than the cores available? Because that may defeat the purpose of parallelization. Because if you have more work than the number of cores available, they have to start working sequentially then, right? And the question is because of latency tolerance. Now if you remember earlier we discussed that in CPUs that if you want to execute an instruction on the logic unit, you need some data, and that data has to come all the way from the memory. So to generate that one cycle of computation, you need many cycles to move the data from your main memory to the caches to the registers on the CPU. So registers is what are closest to the logic unit, so that they can read in within one cycle. So the time or the instructions lost in moving the data is basically loss of time, right? So what if there could be pipelining that could be done? So many WOPs or many threads are scheduled. Now some threads need data, some threads already have the data available in the registers. So whichever threads do not require the data at that time, it's all about time right here. So let's say you generate 32 times more number of threads. Some of these have the data available on the registers, so they will get executed. But while they are getting executed in time, in parallel the data starts moving for the other threads. You understand? Think in terms of logistics. So you have lots of trucks. You don't have trucks equal to the number of the amount of movement you want. You always have trucks which are getting loaded, while one track starts moving. So this loading is equivalent to the instructions, or the data being transferred from global memory, for example, to the registers in the cores. So what happens is the waiting time for warps that would have been there if you scheduled only the warps, or the number of warps or the number of threads equal to number of cores is reduced. So this is called zero overhead thread scheduling. You don't need to remember these terms, by the way, but you may read or go through them in some literature or text. So you schedule the threads in such a way so that there is zero overhead or wastage in terms of the time lost or the cycles lost for waiting for the data. So this is called pipelining, instruction pipelining. So this happens in CPUs also, by the way. We didn't talk about it, but this happens under the hood. So this is some intrinsic level of parallelization which is there within one CPU. So while you are trying to do something, at the same time in parallel the other instruction is getting its data ready. So when the first is done, the second may have been may be ready with the data, and so on. And this is the reason you don't need to dedicate a lot of cache memory on the chip area in GPUs because of this pipelining. What is the point of keeping a lot of cache? Because you are scheduling more threads than the number of cores available on SMs. So when some of them are working, the other may quickly move their data rather than storing a lot of cache. So for example, A100, which is a decent GPU, has 64 cores, as we just talked about, but it can schedule up to 2048 threads. So that's 32 times more than the number of physical cores available on the memory. And when I say schedule, that means at the same time. Of course, if you talk about overall, you can schedule many more. It's all about at a given time. Next is occupancy. Now that's a very important thing. So occupancy is defined as a number of warps assigned to the streaming multiprocessor divided by the maximum number of warps supported. Okay. So let's talk through examples. So A100, NVIDIA A100 GPU can support a maximum of 32 blocks per streaming multiprocessor or 64 warps per SM. So that is, it can schedule 2048 threads or support 2048 threads per streaming multiprocessor. Okay. And it also has a constraint that it can schedule a total of 1024 threads per block. So this is some constraint given by the hardware, you don't need to worry about that. But let's look at our example. So let us say we launch a block with 32 threads each. So you are launching blocks where each block has a total of 32 threads. But because of this constraint, we can only launch a maximum of 32 blocks on A100. Okay, so there is a constraint 32 blocks per streaming multiprocessor. So we can only launch 32 blocks, and each block has 32 threads as you decided for some reason. So that means 32 times 32 is 1024. So what you have done is you have launched 1024 threads, whereas the total threads allowed were 2048. So what's happening is that you have only a 50% occupancy. So occupancy is a standard term. So this means that you should at least be scheduling 64 threads in a given block because of the constraint that you have on the hardware. Now you may think that what is the point of knowing all about this? It's important because you don't randomly choose numbers when deciding the number of blocks and the number of threads per block. It has to be dependent on the hardware. Some hardware may allow more number of blocks for a given streaming multiprocessor. Then this condition would have resulted in higher occupancy, maybe 100%. But in this given case for A100, if this is what you chose, you would only have 50% occupancy. So what that means is 50% of the time the GPU is sitting idle, it's not doing anything. So this is not the best utilization of GPU for parallelization. Okay, so this is another thing to keep in mind, that is occupancy, when deciding on the size of blocks or the number of blocks per grid or the number of threads per block and so on. Now what if you choose a block size of 768 for example randomly? Now this time 3 blocks are possible. So this means a total of 512 threads will be sitting idle. So that is, in this time you have 75% occupancy. Okay. So this is reduced occupancy because of a bad choice in terms of the number of blocks or the number of threads per block. So the first example I showed you was the number of blocks, which resulted in 50% occupancy, and the second is where you chose a non-optimum value for the number of threads per block, which is 768 in this case, that resulted in 75% occupancy for this A100 card that you have. So this was the choice of the grids and blocks. But what about the memory? So we saw kernel function, right? Kernel function is a function which is executed on all the threads or all the cores. So in the kernel function we had something like an automatic variable, like we had the variable idx, which was simply the ID. So that is a private variable. Each thread will have a separate value for it because each thread has to execute a different ID or a different element of a matrix. So this becomes an private or an automatic variable. Again we will go more into details when we talk about memory architectures, but what happens is there is some register memory on the streaming multiprocessor. So register memory is where these automatic variables are stored. So if you have more automatic variables or private variables, then you need more register memory in the given streaming multiprocessor. But there is a limit because the memory is fixed. I mean there is a limit. For example, in A100 you have around 65,000 registers per streaming multiprocessor, and you already know that you can have a total of 2048 threads. So if you write a kernel function, let us say non-optimally, which takes a lot of which has a lot of automatic variables and which results in 64 registers required per thread. Okay, 64 registers are required to store the private variables or automatic variables on each thread. So what happens is the constraint here is not the number of threads now, the constraint becomes memory, because 1024 threads times 64 is approximately equal to 65,000 registers. So even if you wanted, you cannot schedule more than 1024 threads here because you are out of memory in terms of registers on the SM. So this is a memory bottleneck here, that you wrote the kernel function, let us say maybe ineffectively, maybe that is what you had to do, there was nothing else possible. But if you were not caring about the amount of memory you are giving to automatic variables in a kernel, it may result in again lower occupancy. Alright, and this is critical. You have a GPU card which is sitting idle for 50% time, or it is not utilizing the complete resource. What is the point? You could have spent on a smaller GPU card in that case. Now you may ask me that, does it mean I should be moving with a chart all the time which has all the details about GPU cards? The answer is no. Of course you can write a program more smartly. So you have you can query device properties. So you can have functions and variables available which will return the value of these informations that I showed you for a given card that you have on the hardware, so that the choice of number of blocks per grid or the number of threads per block or other things can be based on these device properties that is available to you for the device available to you. So, for example, you may have multiple GPU cards on the machine. So, you have a dev count variable which stores the number of devices. So, in my machine, for example, I have an onboard GPU which typically every Intel motherboard has, and I also have an NVIDIA GPU. So, the dev count will come out to be 2 in this case. Okay. And then you pass this dev count, the reference to it, to the CUDA get device count. So, after this statement, dev counts becomes 2 on my machine. I will show this to you later. So, now for each device, first I have to decide which device is the one I am interested in. So, you have you can print the device name and so on, or the architecture. Then you can have an object called devprop, which is of the type cudaDeviceProp, which will store all the properties of a given GPU card, and then you can loop over all the devices or dev counts, and you can do something with whatever card you want. So, let us look at some of the device properties that are available. So, if you say devprop dot max threads per block, so this tells you what is the maximum number of threads possible per block on this GPU card. If I go back for this A100, for A100 it was 1024 threads per block possible maximum. So, for this A100, this max threads per block will become 1024. So, now you know, so now you can have some formula that will help you decide on the parameters for your scheduling. Next is multiprocessor count, then clock rate, max threads, dim, max grid size, registers per block possible. Well, this is I think the same. So, for example, clock rate. So, clock rate is, we never talked about it, but clock rate is your cycles per second. So, like CPU is doing 3.2 gigahertz, that is a clock rate. So, if you want to know how good a GPU you have in terms of how fast is a given core, then you can read the clock rate, which will be in hertz on cycles per second. Processor count is how many cores do you have per given streaming multiprocessor is streaming multiprocessor. So, how many cores do you have in a given streaming multiprocessor? So, for example, A100 had 64, right. So, 64 cores are available for a given streaming multiprocessor. So, that will be here. So, if you multiply these two values, you get the total amount of flops possible, because you know the cycle per second for one core and you know the number of cores available on a given streaming multiprocessor, then you get the total flops for a given streaming multiprocessor, and then you have queries for finding the number of streaming multiprocessors on the given GPU. So, max threads dim. So, a block has, remember, we can have multi-dimensional blocks in x, y, z directions. So, what is the maximum size of the block in a given direction? It may happen that due to some constraints, the number of threads you can have in a given block in x direction maximum is some value, y is different, z is different. So, you cannot schedule a block or decide on a block size more than this value. So, you have to use these properties so that you do not end up crashing your program when it runs on a given GPU. Right. So, we will discuss or you will use this more in the lectures to come, but I just wanted to give you a flavor of the compute architecture of GPUs. And see, you have done a lot of parallel programming till now in terms of OpenMP and MPI. So, you have all the training to write a parallel program, be it on CPU or a GPU. So, it is important to now understand how to optimize those programs. So, I showed you a program, a 3-step process for writing a GPU CUDA program. if this program was given to somebody who had no experience of parallel programming, I would have spent many lectures to explain that. But for you guys, I just spent half a lecture or one lecture to show you the 3-step process, because you already have a lot of training of CPU based parallelism. So once you have this basic understanding, everything else is about optimizing the program, which requires a very in-depth understanding of your compute and memory architectures. That's pretty much it. And after that, it's all about learning from seeing. So you read programs which are well written, you write your own programs, try to write your own programs, optimize them sequentially through discussions or through sequentially improving. That is how things work. Okay. In GPUs, there is a lot of control over whether you want to send the keep the data on the global memory. Even there is something between global memory and your SM memory. SM has 2 types of memories. So you have all the control over where you want to keep the variable. So this is where things become challenging. The easiest thing is everything goes to the DRAM or the global memory, but that's a little further away from the streaming multiprocessors. So the program may not be as efficient as the one if you had control over where to keep which variable. Now of course that is for you to figure out over time. So let's stop the lecture now.